Hi once again, welcome to video number 162. This one is on similar triangles, and the keywords I've got for you are similar and linear scale factor. So similar means same shape, different size. Linear scale factor is the length scale factor. I won't necessarily refer to it in this particular video, but the next one we will. It's how many times bigger something is. So in the method states to prove that two triangles are similar. This whole video is about the proof of similar triangles. You must be able to show one of three things. The first thing being three angles are the same. Really simple. If all three angles are the same, then the shapes are similar to one another. Or you could show that all three sides are in proportion. All right, so it could be, and that means scaled up. Exactly using the same scale factor, same common ratio, whatever you want to call it, multiplier. Number three, it could be that two sides are proportional and the angle between them is the same. And then you've got to be careful when choosing the condition of similarity. The suits always state therefore similar at the end. Okay, just to round off the question nicely. Now, in number one, you've got the following pairs of triangles are similar. State the condition that proves this. So what I've got in that question there is three side lengths. So I've got 30, 18 and 26. And on the second triangle, 15, 13 and 9. Okay, if you look at this one, 30 is double 15, 18 is double 9 and 26 is double 13. So these are all in proportion. All three sides are in proportion. Okay, so what's the condition that proves it? All three sides in proportion. Or you could say that triangle, if we labeled that one triangle A and that one B, okay, we could say that triangle B is half the size, or the dimensions are half of triangles A's, or anything to that effect would be absolutely fine. Okay, therefore that's a similar triangle to that one. Might not necessarily get asked that, but it's very useful to know how to figure that out. Okay, B, what we've got again is another pair of triangles there. One's been flipped around. What we've got in this one is a side length and another side length here. And you can see that they're in proportion to the side lengths on the other triangle, and the angle between them is the same. Okay, so two sides are proportional and the angle between them is the same. I could write that down there, but I'm just going to highlight the fact that I've called that number 3. And I'm just going to write number 3 there, all right? Because you could think of me writing that down there. I'm sure you could visualize that, couldn't you? I'm not going to squeeze it in that space, right? But that's the condition that suits that of similarity. Okay, and this 6 meters is that's 2 meters, so you times that by 3, you get 6 meters. All right, 80 centimeters times by 3 would be 240 centimeters, which is 2.4 meters. All right, which is why that works. Even though the units is different, it's still the same length. Okay, or at least not the same length, it's 3 times that length. Anyway, in proportion, and angle in the middle is the same. Question 2, shown are 4 triangles, which pair are similar, and state the reason why that they are similar. So let's see, and we've got 3 angles in each of these triangles, so it's going to be the first thing. 3 angles are the same. 60, 76, 44, 60, 74, 46, 70, 45, 60, and 60, 75, and 45. It's 60 or 75, 45. It's B and D, isn't it? They're the ones that have got all 3 angles in the same. They're not drawn to any particular scale, but they are the same. They are similar. Okay, so B and D. Okay, and then it would just be all 3 angles are the same. All right, hopefully that makes sense to you. Now, let's have a little look at the third and final question without getting stuck over there. In the diagram below, AB is parallel to EF. AE and BF intersect at points C. Prove that ACB and CEF are similar triangles. Give reasons for your answer. So, basically, we've got some angles in parallel lines stuff going on, like we did in the congruent triangles question. I've made a very similar one here. Right, this time these are similar triangles, and it's the reason that we've got here. We've got parallel line, a line that goes through it, another parallel line. We've got the Z angle there, the alternate angles. Okay, that angle's the same as that one. Okay, The same on this one. This angle here is the same as this angle here, right? Because of the Z angle fact, the alternate angles. And then what we've got are two sides here and two sides here. All right, so actually we're not really worried about the one that I shaded in over here, this angle. We're just interested in this 0.6 meters, okay, 2.6 meters, 130 centimeters doubled would be 260, wouldn't it? So hopefully that's definitely 2 times bigger. That length there is this one 2 times bigger than this one. Well, that would be 60 centimeters. 60 centimeters is double 30 centimeters. Not sure why I'm not really writing that on there. Okay, there you go. So two sides there are in proportion, and the angle in between them is the same. Okay, and that's our proof. We could call that X if you wanted to give it a name. Okay, but angle BAE is equal to angle FEA. Okay, and that's because they're alternate. Okay, CE is equal to 2 lots of AC, and FE is equal to 2 lots of AB. All right, putting that 2 in front of these means that that's just 2 times whatever that length is. Okay, and therefore similar, and the reason again, 2 sides are proportional. And the angle between them is the same. Okay, so there you go. There's all of that information that you need to be able to understand this particular topic. Now, it gets more interesting than that. We're going to be able to find missing side lengths in the next one. This one was just about proof, and maybe not necessarily going to be asked questions on this, but it's a skill you need to understand in order to be able to work out missing lengths. Anyway, so thanks for watching. I'm going to cough in a second, so I'm going to finish this video now.